Hi everyone, it's my great honor to present our work. I'm Zicheng Wang from Nanjing University, and my co-authors are Professor Yueqi Chen from University of Colorado Boulder, and Qingkai Zeng also from Nanjing University. The vulnerability life cycle consists of 4 main steps. The vulnerability introduced, and discovered, and patched, merged, and deployed. On the left of the figure, tools such as sense caller and static analysis, they are developed to discover kernel vulnerabilities. And on the right, after the patch is available, the vulnerability can be fixed. So apparently there is a time window of at least 66 days between discovering a vulnerability and a patch availability, which the kernel is left vulnerable and unable to protect itself from exploitation. So this motivated us to present our work, prevent discovered errors from being triggered. In most cases, a vulnerability on the error side is triggered by a malicious process through system call. And after the attacker triggers a vulnerability, the entire kernel will be compromised. Our solution, PAD, is to prevent the vulnerabilities from being triggered. PAD takes the sanitizer report as input to locate the error site and condition, and generate a BPF program to nip the threats in the bud. The BPF program will be executed every time before the error site and check if the current context meets the triggering condition of the vulnerability. If not met, nothing happens, kernel will keep functioning. And if the triggering condition is met, the BPF program will help the kernel skip the error site and jump to the return of the function and send signal kill to stop the malicious process. After that, the kernel will keep functioning. Because PAD focuses exactly on the accurate error set rather than the entire kernel, so it's lightweight and efficiency. We will introduce first what is eBPF. PAD is built on the eBPF, the extended Berkeley filter framework. It's an in-kernel virtual machine that allows users with root privileges to load programs into the kernel space. The framework contains 3 essential components. The verifier to provide security guarantee for the loaded program. The GT engine optimizes performance by translating the BPF bytecode to the machine code. And the helper function provides expressive interface between the BPF program and the kernel subsystems. Most important, BPF also provides hook mechanisms based on kprobe. It can attach on arbitrary error sites in the kernel without recompiling or rebooting the kernel. PAD leverages these powerful capabilities of framework to detect and prevent the kernel vulnerability with high efficiency. Next, we'll show a working example. Here is a slab or heap out of bound in the kernel. The error condition is shown in the line 645, where the length of array args is defined as size in the function arguments. So the last index can be written as size -1. But the code mistakenly writes the index size, resulting in 1 byte overflow. And PAD generates a BPF program to check if there is an overflow at the error site. If the triggering condition is met, and the BPF program helps the kernel to skip the line 645 and jump to the line 693, returning an error code. This makes the kernel believe that the function has failed, and execute the error handlers in the call stack until it returns to the system call. We have designed a layered architecture to achieve the design goal. The underlying layer is error-independent mechanisms. They provide the tools and mechanisms to support the policies. It includes the report processor, the sanitizer to native kernel mapper, and checkpoint restore analyzer. The overlay error-dependent prevention policies are designed based on the triggering condition of each type of vulnerability. PAD provides templates of BPF program for automatic generation. PAD can be extended to more types of kernel vulnerabilities as long as there are proper policies. First, let's talk about the mechanisms. The top of the figure is a sanitizer report. We can get the report by executing vulnerabilities proof of concept program. In the sanitizer kernel, we can see the error type in this figure is slab out of bound, and the error set is farmer set proc attribute. plus an offset. The report processor is a Python script with regex to help us extract the information. After that, the sanitizer kernel is instrumented and totally different with the native kernel. So the sanitizer to native mapper translates the error set from sanitizer binary to the source code and to the native kernel binary. Normally, we can use address to line to map the binary address to the source code lines. But the address to line is well known to be inaccurate. One address can often map to more than one line of code and vice versa. So our solution is use address to line and variable to register two translation flows for cross-check. And both the translation flow can be obtained from devolved debug information. The false positive number is reduced to 0 per case use our method. The next component of the underlying layer is the checkpoint restore. It set up checkpoint to record the register as the function entry. When the error condition is met, it helps to jump to the function exit and restore the register context, assign an error code to REX as the exit. And the rest function in the kernel call stack will treat this function failed in the execution and leverage their error handlers to keep the kernel functioning. The checkpoint restore is a temporal workaround rather than a sound solution because there are about 500 pairs of operations and troublesome state spill, such as a file read or write, the device operation, the locks, memory allocation, global memory modification, etc. Our work temporarily focuses on solving the locks and memory allocations because other pairs may not corrupt the kernel. Also, because the distance between the function entry and the error set is close, so there is nearly no complex situations. We test the robustness of our solution by execute the kernel working on daily tasks for weeks. Nothing serious happens, the kernel still keep functioning. After the mechanisms, let me introduce the overlay error-dependent prevention policies. Policies are designed based on the error condition of each type of the vulnerability. For example, here in the left, the out-of-bound policy, the address of a pointer plus an offset must be in the pointer's legit range, otherwise the error is being triggered. So to help obtain the range in the right, PAD provides get buffer start and length BPL helper functions used in the template for automatically generation. And the policy can be extended to other types of vulnerabilities, such as integer overflow, data race. The rest can be found in the paper. Although most policies are straightforward, the use-out-free vulnerability policy are complex. It's a temporal memory corruption. The triggering condition of UEF is that the dangling pointer is a pointer referred to a freed object. And dangling pointer is dereferenced to read or write a freed memory. So the use after free policy is quarantine the freed object until no dangling pointer exists. And sweep periodically the entire physical memory for dangling pointers. We also design an optimization that sweepers only need to sweep the certain step cache because most dangling pointers are stored in a special step object. We collect set caller reports and CVEs to evaluate our work. First, we evaluate the effectiveness as shown in this sample result table. The black circle means that BPL program can prevent the error and keep the kernel functioning after the prevention. The half black circle, as we can see in the bottom, means under an aggressive prevention policy, even one single byte memory uninitialized will be treated as uninitialization and skip. It somewhere hurts the kernel functioning. The performance overhead is measured by executing the BPL prevention programs and the benchmark programs at the same time. The table shows the result compared to the vanilla kernel. The average overhead is negligible, less than 3%, and compared to the fuzzing optimization work and do workaround, the overhead makes no significant difference. Scalability means the performance overhead when execute multiple BPL programs at the same time. In the figure, each line represents a benchmark overhead. When apply more than 20 BPF program, in most cases, the worst overhead is less than 8%. But there are special cases that a BPF program hook on the NAPI network interface, which is called very frequently under high concurrency web server requests. We also evaluate the optimal sweep period and range in the UAF whole physical memory sweeper. The range is from 128 megabytes to 512 megabytes. The period is from 1 second to 8 seconds per second, and the machine has 60 gigabyte memory in total. Apparently, the optimal is 256 megabytes every 4 seconds. In conclusion, our work presents PAT, a framework to protect the kernel before the patches are available. It supports error-dependent prevention policies and error-dependent mechanism to support the policies. We also make a thorough evaluation of our overhead and scalability. Next, I want to show a demo. We start a virtual machine with it's clear. With two terminals. On the left terminal, we run proof of concept programs. And on the right terminal, we run all the BPF prevention programs and monitor the output. First, in the right, we start all the BPF prevention programs. First, we execute a integer overflow vulnerability. As we can see in the right, the integer overflow is caught, and in the left, the process is killed. Next is a out of bound. The process is killed and the vulnerability is caught. The next is a use out free. We can see the dumping pointer is quarantined. And last is the initialization. We can see in the right, the initialization is stopped. So after that, we can see the kernel is still keep functioning. Thank you so much. Any questions?